Welcome back, class. Today we're going to begin our discussion of mathematical language. And so we're going to work on understanding sort of complicated statements like the following. For every n in the positive integers, there exists a p in the positive integers, such that p is prime and p is greater than n. There are a lot of things going on here. So first of all, I should notice there's a lot of connecting phrases here, like and such that. And we're going to talk about exactly what mathematicians mean when they use a word like and, or if, or then, or all of these various things. That's sort of the first piece we're going to talk about. The next thing I want to draw your attention to is the fact that we have these things floating around. These are references to what we'll call sets. And you've probably seen sets before. They're collections of various objects. In this case, z plus is just the way we'll denote the positive integers. But we'll talk quite a lot about sets in this class and learn all sorts of things about them and the notation for them, etc. Lastly, we have these two pieces that I will underline in green. These are the statements for every and there exists, and these are called quantifiers. The quantifiers describe exactly what we're saying about these elements of the set. So this first one, we're talking about something that's true for every n in the positive integers, and then over here we're describing that we can find a p with this property, as opposed to every p having this property. And all three of these pieces, the quantifiers, the sets, and these connecting words, these are things that aren't really related directly to the mathematical content of this statement. These are really just the logical connectors for this. All of the mathematical content in this statement lives in this bit where I say p is prime, so you know what a prime number is, but that's sort of buried in here. And p is greater than n. This is something you've known for a very long time, what it means for one integer to be greater than another. But all of the sort of quote-unquote math part is buried in these two pieces. The rest of this is the connecting stuff. And so our goal here when I talk about mathematical language is for us to understand how to use and read all of these various connecting pieces. Now, since we're starting, I might as well take a second. What does this actually say? So I'll let you pause if you like and think about this for a second. But what this mess actually says is exactly equivalent to the statement that there are infinitely many primes. So this is the theorem of Euclid from 300 BCE that we talked about in the last video. And hopefully by the end of this week where we talk about all of these pieces, if you don't see now exactly why that's what this says, you'll see it by then. So we're going to start by defining what a mathematician means when they talk about a statement. And so in this course, whenever I'm defining something, I'll write it like this, def colon, underline usually. So a statement is a sentence, or sentences, that is unambiguously true or false. And note, something like 3 plus 5 is 8. This is a sentence. This equation, every equation is a sentence. The verb is equals. And so this is saying 3 plus 5 is 8. This is the subject, etc. So equations can certainly be statements. Both of these things, so far, are statements. This one happens to be true, this one happens to be false. But things like this, 121 is prime, pi is irrational, these things are statements. Now, I want to note, you don't have to know whether the thing is true or false in order to know that something is a statement. So, for example, 1000 factorial plus 2 to the 131st power plus 7 is prime. This is a statement. I don't happen to know whether it's a true statement or a false statement, and I somewhat doubt you do either, because I at least arranged that this number is odd. But it's ridiculously gigantic, and probably you don't want to go to figure out whether it is true or false. I just know that it is unambiguously true or false. And so the essence of this lives in the word unambiguously. We need to make sure when we're talking about statements that there is no possibility that it's unclear whether the thing is true or false. Now, I want to make a side note, and my side note is that logicians usually call statements propositions. And for that reason, the section of the book that we're talking about, and I'll say some words about the book in a second, is called Propositional Calculus. So the idea when you see propositional calculus is that you're supposed to imagine that I'm doing the regular sorts of arithmetic, but with propositions instead. So sticking the word and between two propositions, or just figuring out how all of these basic ideas about truth happen to work. You will never hear me use the word proposition to mean statement in this class. And here's the reason why. Mathematicians inevitably use the word proposition to mean statement that has been proven true. So this would be in direct confrontation with the logician's use of proposition to just mean thing that is true or false. So I'm not going to use that. In fact, you'll see that lots of words get used in different ways in different places, and the same is true for notation and all sorts of things. And so you'll see in this course, I'll always try, rather than to get into the middle of one of these disputes, where people use this word in one way and other people use it in the other way, and pick a side, I'll always try and pick something where everyone will agree what the word means. And if it's at all unclear, if I think there's any chance of people disagreeing, I'll be careful about it. But generally, rather than picking sides, our goal in writing and talking should be communication, and so it's best when communicating to do so in a way that does not confuse the reader. Okay. Third consecutive aside. There is a book for this course. It is by Stephen Galovich, and it is called Doing Mathematics. We have the second edition. It's available in the bookstore, and it is optional. You probably don't know this, but textbooks at the bookstore fall under 3 tiers: required, recommended, and optional. And their severity is in this order. So I deliberately picked the lowest possible one. If you want a book, I think this is the best book that I'm aware of that covers this material. I think many students have gotten by this course without the book. You're welcome to purchase it if you like. I will always refer to sections by the section number in the book, and I will broadly follow the order of the book with one exception that I will advertise clearly, so you can make the decision for yourself. I do think the book is a bit expensive. I wish it wasn't, but here we are. If you want a book to read, it's a good choice. So that was a long string of asides. Let's get back to talking about statements again. And let me give you some examples of things that are not statements. 5,300 is a big number. There is no well-defined sense of what it means for a number to be big. So there's potential for disagreement. Someone might think that 5,300 is a big number. We talked about a number that was on the order of 10 to the 50 millionth power last video. That was probably something that most people would agree is a big number. But again, there is no well-defined sense of what it means to be big. So this is not a statement because it's not unambiguously true or false. Here's another example that might get you. Because if someone asked, hey, is it true that pi is approximately 3.1415? I think almost immediately your reaction would be, well, yes. But if you were really forced to ask yourself, what does this approximately equal mean? You might start to realize it's not super well defined. And so you might say, well, I'm certain pi is approximately 3.1415, but then what if someone asks, well, hey, is pi approximately 3.1? What if someone says pi is approximately 3? What if someone says pi is approximately 4? Are these true? Who knows? And so, again, these are not rigorously defined concepts, and so they're not going to make statements. Before we move on, I want to talk about something that shows up in probably just about every math class you've ever seen, which is that we use variables when we talk about math. So we might talk about something like n is even, or f is differentiable, or a is invertible, if we're talking about matrices or whatever. So let's ask, is the string of words n is even a statement? Is this unambiguously true or false? And here, unfortunately, the answer is it depends. What does it depend on? Well, it depends on the context of what n is. If we have no idea what n is, then it's definitely not a statement, because if I don't know what n is, I don't know whether n is even. But if I know that n is a particular integer, so for example, if n happens to be 100 factorial plus 6, then I do know that n is even is a statement, because then I know exactly what n is. I want to be just a tiny bit cautious here, because you will often hear mathematicians say something like, if n is even, then n squared is even. And in some sense, you're inclined to think this string of words is true. But when you interpret this string of words as true, you're adding context that is not there. Namely, you're really sort of trying to imagine, okay, if n is even, what you're really thinking here is if n is an even integer, then n squared is even. And so you're filling in some gaps. And those gaps you're mentally filling in, those are what we're going to use quantifiers for later this week. So really, to make sense of this, we have to use quantifiers. So I promise we'll talk about that soon. Notation. By the way, always when I write colon, I know it sort of looks like I'm saying the thing's not true, but this is just my way of saying notation. It just happens to be the 3-letter abbreviation makes the word not. We'll typically denote an arbitrary statement by the letter P. And then if we have another one, be Q, R, and so on. Usually this is the convention mathematicians will go with. They'll pick the first letter of the thing they're talking about, which in this case, it's the first letter of the word proposition rather than the first letter of the word statement, because S's look like 5s. And then for the subsequent things, we'll just go with the letters after that in the same font. Sometimes you go backwards. So for example, vectors, if you've taken 253, you usually denote the first one by V, because vector starts with V. But then if you want a second one, you go backwards to U for some reason. So people aren't always consistent. But this means I might, for example, write something like this. And what this means here is P is the statement 11 is greater than 4. Or Q is the statement pi is a rational number. So our goal in this section really is to discuss how to make new statements from statements we already have. The first way to do that is to take a statement and negate it. So the negation of a statement, P, is the statement P is false. We usually denote this by something like a squiggle in front of P. So this will either be a squiggle in front of P, or some people like whatever, I don't even know what the symbol is called in front of P. But some people like this symbol in front of P as well. I'll usually use this one in this course. So the way we'll describe each of these new ways of making statements is to say what they do in terms of whether the original statement was true or false. So I'm going to make this thing called a truth table, and it's going to look like this. And so in the first column, I'm going to tell you what P is. Namely, is P true or is P false? And note, the truth value of the negation of P will not change no matter what true statement P is or what false statement P is. So if the true statement is 11 is greater than 4, or the true statement is pi is irrational, or the true statement is there are infinitely many primes, it won't change whether the negation of P is true or false. So this column tells me what P is. If P is true, then what's the negation of P? Well, the negation of P is the statement P is false. But importantly, nothing can be both true and false. It can only be one or the other. So if P is true, P is not false. And so the statement P is false is false. And so the negation of P is false. If, on the other hand, P is false, then the negation of P is false, and that is now true. And so this little table here is just explaining to you how negation changes the truth value of a statement. And really all this table is telling you is the negation flips the truth value of a statement. So it flips trues to falses, it flips falses to trues. Negation is the only thing we're going to do that starts with one statement and gets us a new statement. But we're going to talk about 4 ways to combine 2 statements. Okay, I'll call those statements P and Q. The 4 we're going to talk about are P and Q, P or Q, P exclusive or Q, and P implies Q. And most of these have some subtleties, but the nice thing is I can capture all of those subtleties in a truth table. Now, you'll notice when we only were talking about one statement, the truth table had 2 lines. That's because there were 2 possibilities. Either P was true or P was false. When we're talking about 2 statements, there's going to be 4 rows because there are 4 possibilities. Both are true. P is true, but Q isn't. P is false, but Q is true. And they're both false. You can write these in whatever order you like, but your truth table, if it involves 2 things, is always going to involve these 4 rows. So let's start with the one that I think means the thing you think it means, which is P and Q. And really, when you say P and Q, what you really mean is P and Q are both true. So if P and Q are both true, then it is true. However, if either of P or Q is false, then it's not true that both P and Q are true. And there's no double negative canceling sort of business. If they're both false, it's definitely not true that P and Q are both true. I'll note you'll occasionally see people, not me, denote this with a symbol that looks like this, or that. Again, I won't use these. I encourage you, and you'll see this throughout the course, I encourage you to always use words rather than symbols when you're talking about these logical operations to make things easier to read. But just to warn you, these things are out there, and so you'll see them now and then. Next up, let's talk about P or Q. And this is really the statement, P or Q is true. That's definitely not true if both of them are false. On the other hand, it's definitely true if Q is true and P is false. It's definitely true if P is true and Q is false. And the one that can give people trouble because we actually use the word or in 2 different ways in English is whether it's true if both P and Q are true. And the important thing I'm here to tell you is that to a mathematician, ors are always inclusive. Meaning that to a mathematician, P or Q is always true if both P and Q are true. The way that it's often used in English is often to present a choice. Would you like A or B? And usually if a waiter, for example, asks you, would you like soup or salad? You're implicitly not being given this option that you want both. You're being really given an option between these 2 lines. You'd like soup, but not salad, or salad, but not soup. But again, for mathematicians, we always include this option when we refer to the word or. Now, thanks to computer scientists, who would usually prefer the other kind of or, we have a very helpful name for that as well, and that's called exclusive or, although it is often pronounced zor, if you see it read out loud. And this is the or except that you don't allow both. So this is maybe the more traditional definition of or. And so you're welcome in any mathematical statements. If this is the thing you want, you can always use XOR. And as you'll see later, it makes life way nicer if you have that as an option. This is P implies Q, and implication is really the foundation of all of mathematical reasoning. And as such, there are a lot of different ways to say this same thing. So we can say P implies Q. You'll sometimes see people use this implies arrow, although this will probably be one of the only times you ever see me write it. But we also might say, for example, if P then Q. That's probably the most common construction. But we'll see that mathematicians have a lot of different ways to express this idea. But what is this idea? Well, this idea is that as soon as P is true, we know Q is true. So the first two lines here, we can kind of make sense of. So if P is true, then Q is true. That statement about the relationship between P and Q is definitely satisfied if both P and Q are true. But again, you might think of it as long as P is true, so is Q. And if you think about it that way, it's pretty clear, okay, if P is true but Q is false, that's definitely not satisfying the condition as long as P is true, so is Q. The next two, you really have to lean into this as long as to have make sense. Is it true that as long as P is true, then Q is true, if P is false and Q is true? And the answer is, to a mathematician, yes. And the reason is because we don't even get to the as long as P is true part, and so there's no way for this to be false. So it's true. And it's just as true if both P and Q are false. As long as P is true, Q is true, P is false, then it's automatically true. Now, there are a lot of reasons to not love this convention. Here's one reason not to love this convention. If I write down the statement, if 7 is even, then pi is equal to 100, this statement is actually a true statement. Why is this a true statement? Well, this is a true statement, again, because here we are in the 7 is even, pi is 100. Both of these are false, so that's the false-false line, and we see that that false-false line comes across as true. So this takes some getting used to, but I promise that ultimately, once we put all of this together with proofs and quantifiers, this could be no other way. But here's, I think, the easiest way to remember this. As soon as P is false, the implication is automatically true. And as soon as Q is true, the implication is automatically true. The only way for the implication to be false is if P is true, but Q isn't. That's the only way for this idea that as long as P is true, so is Q, the only way for that to fail. So really, this table describes for you all of these notions completely. Because all I need to know, if I have two statements that I already know whether they're true or false, all I need to decide whether the new statement is true or false is what to do in all four of these possibilities. Now, I've left room here to fill in one more thing that mathematicians often use, and this is really just a shorthand. And if you want the super fancy name for it, this is called the biconditional. It's shorthand for P implies Q and Q implies P. Notice this itself is just using my definition of implies and my definition of and in this sort of complicated way to form a new statement. And it might help you, just to make sure that you know what's going on, to think for a second, when is this true and when is it false? Because again, this thing just represents this. Okay, so is it true if both P and Q are true? Okay, so this would be true implies true and true implies true. True implies true is true. True implies true is true. True and true is true. So this is true. What if P is true and Q is false? Well, then P implies Q is false. Q implies P is true. But false and true is false. So this is false. What if P is false and Q is true? Well, then P implies Q is true. But Q implies P is false. So this is true and false, and that will be false. What if both P and Q are false? Well then, P implies Q is true. Q implies P is true. So both of these are true, and so it's true. That means at the end of the day, what this biconditional is really saying is that P and Q have the same truth value. Because you'll notice this worked out to be it's true when P and Q are both true, or when they're both false, but it's false otherwise. I'll go ahead and note, when we want to say this in words, we often say this out loud as if and only if, so you'll see P if and only if Q. However, that's a lot of letters to write down, and mathematicians tend to like saving letters whenever they can. And so even in professional writing, though this drives me crazy, you'll often see people write this, where this if word that has two F's is meant to stand for if and only if. So if you ever see a textbook or a professor write this IFF word, they're trying to communicate the biconditional between P and Q. Now, as I said, a lot of this course is going to come down to discussing and carefully understanding this notion of an implication. And so the first thing we really want to understand is that implications are directional. In particular, P implies Q and Q implies P are different. And we now have a really solid way to understand the fact that these are different. Namely, we can write out a truth table for both of these. I really recommend pause the video, write out these truth tables for yourself. It'll just take a second. Make sure you understand the difference between these things. But I'll go ahead and do it for you. True implies true is true. True implies false is false. False implies true is true. False implies false is true. Now, Q implies P. That would be true implies true, so that's true. This would be false implies true, so that's true. This would be true implies false. That's the false one. And this would be false implies false, which is true. So the key thing here lives in these two lines. It lives in the fact that these two things work differently if you interchange P and Q. For this reason, we really need to distinguish whether we're talking about an if statement, an only if statement, or an if and only if statement, whenever we're talking about these things. So this would be read as P only if Q, potentially, although I would probably say P implies Q rather than saying only if Q. And this would be read as P if Q. So when we say P if and only if Q, we're really putting these two together, getting us this simple as we're used to. So for every implication, it makes sense to ask about the implication the other direction. And we give that implication a name, namely we call it the converse of the original implication. So as you learn more and more math, you'll learn more and more theorems, and inevitably those theorems will have the form if something, then something else. So really, almost all theorems take the form of an implication. And for any theorem you learn, it is a question that your professor will ask, or you will ask, is the converse of this theorem also true? Sometimes it will be, sometimes it won't be. And it'll be interesting to think about exactly how that works out. In addition to the converse of an implication, we also have what's called the contrapositive of an implication. And the contrapositive of the implication P implies Q is the implication not Q implies not P. Now, the converse was a very natural thing to write down. You might wonder, why would anyone ever think to write this down? And the reason why someone would want to write this down is something we can discover by looking at the truth tables here. Okay, so let's quickly fill out a truth table where we're going to fill in all of these pieces. We know our implication. Hopefully we're getting this internalized. Okay, not Q should flip Q, so this should go false, true, false, true. This should flip P, so this should go false, false, true, true. And then not Q implies not P. This will be false implies false. That's true. True implies false. That's false. False implies true. That's true. True implies true. That's true. Again, there's something important to notice here. And that thing that's important to notice is that this string, TFTT, is exactly the same as this string, TFTT. And what this means is that although the converse of an implication is different than the original implication, the contrapositive is not. And so here is an important fact that we have just proven. An implication is always logically equivalent to its contrapositive. And what that means is, if you want to know if an implication is true, you can answer that question by asking whether its contrapositive is true, because the answer will always be the same. This will be particularly useful in a week when we're trying to prove implications, and it will often turn out that it is far easier to prove the contrapositive of an implication than it is to prove the implication itself. And so a common proof technique that we'll employ will be to replace a statement by its contrapositive and then prove that. And because the contrapositive and the implication have the same truth value, that will be enough to prove the original implication. Now, so far it hasn't really felt like we were doing calculus with any of these symbols. We haven't really been mushing them together and distributing or whatever. But now we're going to talk about that. And so we're going to talk about what happens if you, for example, take the negation of P or Q. In other words, how do I distribute this negation across this OR? Now, there's no super clean way to do this other than to write down, again, the truth table. And we see that not P or Q gives us this string, false, 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 true. Note, there are going to be lots of coincidences, that is, lots of different ways to express the same idea, because there are actually only 16 ways to fill out this truth table. 2 times 2 times 2 times 2. So there's going to be tons of different things that end up being the same. But it's going to be really helpful for us to know what's the simplest way to express not P or Q. And here, it might be really helpful in thinking about what we want to look for to think about how many truths there are in a particular column. So ORs always have 3 truths. This not P or Q only has 1 true. We can look back at our table. Where was there only 1 true? Aha, there we go. There's only 1 true in P and Q. Now, notice P and Q is not the same as not P or Q, because the true is in the wrong place. But I can actually fix that. Namely, this is actually the same thing, and I'll let you check this. This is the same thing as not P and not Q. So again, how do you check this? Well, I look over here If P is true and Q is true, not P is false, not Q is false. False and false is definitely false. Again, P is true, Q is false. Not P is false, not Q is true. False and true is false. P is false, Q is true. Not P is true, not Q is false. True and false is false. P and Q are both false. Then not P and not Q are both true, and true is true. And so again, you see here in this table, spelled out for you right away, that these two are different ways of saying the same thing. And this is the first of what's often called De Morgan's laws. The first of which is that not P or Q is always equivalent to not P and not Q. What's the other of De Morgan's laws? The other of De Morgan's laws explains what happens when we take not P and Q. And I'll leave it to you to check this, but not P and Q is equivalent to not P or not Q. So these are very useful when it comes to thinking about negations. Now, why is it you might be thinking about negations? Well, you might be thinking about negations because you want to write down the contrapositive of a somewhat complicated implication. And so, to wrap up this section before I unleash you on the homework to work on this and think about this, I want to write down a few contrapositives. This will sort of put together all the pieces that we've talked about today. So here we have a statement from geometry that you might recall, which is that if all the angles of a triangle are different, then all of the side lengths are different. So this is a classic if-then statement. So here's the if piece. And here's the then piece. So when I go to write down the contrapositive, well, I need to write down the word if, then the negation of this, then the word then, and then the negation of this. So what is the negation of the statement, all the side lengths of a triangle are different? Now, here's something where you might be inclined to say, well, the negation of that is all the side lengths of a triangle are the same. However, that is not the negation of all the side lengths are different. And here's where it's important to remind you that the negation of a statement isn't the opposite, in whatever sense that means. In fact, opposite would be one of those things that's not really super precisely defined. But the negation is super precisely defined. Namely, the negation of all of the side lengths are different is the statement that the statement all of the side lengths are different is false. How many ways are there for the statement all of the side lengths are different to be false? Well, it could be false because all of the side lengths are the same, but it could also be false because two of the side lengths are the same. And so there are a few ways I could write down the negation of this, and here's how I would do it. I would say the negation of this is if at least two of the sides of the triangle are equal. But if you preferred, you could, for example, say if the triangle was isosceles or equilateral. So, in other words, the negation of all the side lengths are different could also be written as the triangle is isosceles or equilateral. So I write down the negation of this piece, followed by the negation of this piece. And so now you can probably figure out what's the negation of all the angles of a triangle are different. The negation there is at least two of the angles are the same. Now, the exercise of writing down the contrapositive of an implication has nothing to do with whether anything involved is true or not. But just for the record, you can take a second to think, is the original statement true, and is the contrapositive true? And in fact, these should both be familiar statements, and they're both true. And note, because they're logically equivalent, as soon as I tell you either of these is true, the other is automatically true. This one's a little simpler. I really would encourage you, pause the video for a minute, try and write down the contrapositive of this, and then I'll talk about it, of course. Okay, so we have two pieces here, linked by an if and a then. If p is prime, then p is odd. So when I go to write down the contrapositive, I first have to write the word if, and then I have to write the negation of this piece. And what's the negation of p is odd? Well, if p is not odd, then p is even. And now I have to write down the negation of p is prime. I'm going to write down here p is not prime. Now, why am I saying not prime instead of composite? And the reason why I'm saying not prime instead of composite is that if we look at the positive numbers here, we have these ones are prime, these ones are composite, but one is annoyingly neither prime nor composite. So just as an aside, if you want to write down the negation of p is prime, that's really going to tell you either p is composite or p is 1. So that'll come up a couple times, but it's not really relevant. It's just why I did this. Okay. So recap, when we're writing the contrapositive, again, we flip the order and we negate both pieces. Okay, so we negated p is odd, put that first, negated p is prime, put that second. Now in this case, in fact, this implication originally is false, right? Because 2 is prime. And it's not true that if 2 is prime, then 2 is odd. That would be the 2 is prime is true, but 2 is odd is false. So that's the true-false combo that makes an implication false. So this original implication is false. Which means if you believe the original implication is logically equivalent to the second implication, that it should also be false. And it's false for almost exactly the same reason. Namely, we can take p as 2, and then we see if 2 is even, then 2 is not prime, and that combination is very bad, right? Because again, 2 is even, that's true. 2 is not prime, that's false. And so that's, again, the false implication combination. Here, I have taken a statement from our real analysis course. And probably you know what almost none of the words in this statement mean. But the beauty of the fact that in this chapter, we're only talking about the connecting logic between these various pieces is that you don't need to know what any of these words mean in order to write down the contrapositive of this statement. Again, I would encourage you to be brave and try and write it down before you watch me do it. So again, negation of S has an accumulation point. If S does not have an accumulation point, then, and now I'm supposed to negate the statement S is bounded and infinite. And so it's really tempting here to say S is unbounded and finite. But what did I do wrong? The thing I did wrong with what I said out loud there is that I did not apply De Morgan's laws. Namely, I am negating the statement S is bounded and infinite. And so that and in bounded and infinite is going to turn into unbounded or finite. In particular, the and flips to an or because of De Morgan's laws. So to finish this, then S is unbounded or finite. Again, we don't need to know what any of these words mean in order to write down the contrapositive here. This is, in some sense, a really raw arithmetic process. We're just applying these various rules of how ifs and thens and nots and ors and all of these things fit together. I promise we'll get to actually understanding these statements later, but for now, we're going to be content with writing down these contrapositives. All right, I'm going to wrap up this video here. In the next video, we're going to start talking about sets and set operations, which are going to connect back to these notions of and or, and which are going to be used as an important piece of our puzzle when we start studying quantifiers at the end of this chapter. But that's all for now. I'll see you next time.